Today's going to be kind of like that spot where we learned how to take the derivative with limits. It's sort of going to be that intermediary step before we get to what we do more generally to find these areas. So today, what are we going to do? We're going to use a Riemann sum to calculate the area under a curve. How are we going to do this? We're going to use a summation to model the area and then take the limit as n goes to infinity. Why are we going to do this? Well, we don't want approximations. What we want are actual answers. And this is going to be sort of the first step into doing that. So let's go ahead and look at some stuff. First of all, sums. When we want to add a bunch of stuff together, sometimes it helps for us to write it in a more compact way. Now, of course, we don't like to actually calculate with this, but this is a way for us to write it so we're not writing a whole big long thing. So what is it that we're actually doing with this thing? So basically, we're adding up a bunch of terms. We're adding up all the terms from 1, in this case, to 2. So there's 2 terms, right? Term number 1, term number 2. And for term number 1, whenever you see a k, you put 1. For term number 2, wherever you see a k, you put a 2. So let's actually write this out so we can see what it is that we actually have. So for term number 1 of this summation, we've got 1. So 20 times 1 over 1 plus 3, right? And we'll simplify this in a second, but let's write down the second term too. 20 times 2 over 2 plus 3. Okay, so we did that. Let's simplify it so that we can have something that's okay to work with. So 20 divided by 4, well, that's 5. 40 divided by 5, that's 8. And so we end up with the final answer of 13. So this summation, when all is said and done, what this equals is 13, right? We're going to do a bunch of these. So here's another one. So we're going to write the sum out, and then we're going to figure out what it is. So now we're doing all the terms from 1 to 5. So there's going to be 5 terms. And wherever we see a k in here, we're going to replace it with the number of the term. So cosine of 1 pi plus cosine of, now the second term, cosine of 2 pi. And then the third one, and then the fourth one, and then the fifth one. And so now we're going to just add all these up. So what is cosine of pi? Negative 1. What's cosine of 2 pi? 1. 3 pi? Negative 1. 4 pi? 1. 5 pi? Negative 1. So we're going to add all these up. Negative 1 plus 1 is 0. Plus negative 1 plus 1 is 0 plus negative 1. So this whole sum adds up to negative 1. These 5 terms, when you add them up, you get negative 1. That's all it is. All right. So now we're going to go the opposite way. Well, I want to take 1 plus 3 plus 9 plus 27 plus 81 plus 243, and I want to write it in this summation sigma notation. By the way, this symbol is a Greek letter sigma, which is the Greek letter S, right? So what's going to help us to sort of see which one of these is right is let's actually break them down. Let's look at them. Well, When k equals 1, this is 3k to the 0. Well, that's 1. When k equals 2, 3k to the 1, that's 3. When k equals 3, 3 squared is 9. When k equals 4, 3 to the third power is 27. Then the next one's 81, and then 243. So this one does, in fact, you could take this and write it like this. Basically saying that this first term is 3 to the 0 power. Well, how are we going to express that? Well, if it's term number 1 and we want it to the 0 power, we'll do the term minus 1 to get 0 up here. This is 3 to the first power. That's the second term. 2 minus 1. Third term is to the second power. 3 minus 1. Right? And so on. So that's one way of writing it. Now let's look at this one. Same number of terms. Here they went from 1 to 6. Here they're going from 0 to 5 of 3k. Well, now let's try it this way. 3 to the 0 power, well, that's 1. Now let's do the first term. 3 to the first power, well, that's 3. To the second power, to the third power, to the fourth power, to the fifth power. And so I guess you notice it's the same thing, right? This is also a way you could have written it. Here, instead of having the terms be numbered 1, 2, 3, 4, 5, 6, they're numbered 0, 1, 2, 3, 4, 5. And here they're numbered -1 to 4. And notice the only difference has been this exponent went from k minus 1 to k plus 1, right? And you know it's going to come out to be the same thing, right? When you plug in -1, you get the exponent is 0. When you plug in 0, the exponent is 1 because it's plus 1 each time. So all three of these are different ways of writing the exact same thing. Okay? So let's move on. Let's do more examples, get a feel for what's happening here. Now here, I'm not even giving you possibilities. We're going to actually try and do this ourselves, right? So let's think about this. We want to rewrite this in a way that indexes these numbers and they tell us already use 1 as the lower limit of summation. So k equals 1. It doesn't matter. So the number, the letter down here that you use, I see K, I see I see J all the time. Those are all fine. I sometimes see N, although that gets confusing because people use N for stuff in here too. So I would say they're gonna give you usually a specific prompt, but on your own, if you want to use pretty much any letter, any variable for what's down here, as long as you keep all your variables different, you're not going to have as big of a problem. But generally speaking, the variable that's used as the indexing variable down here is usually I, J, or K. But it doesn't actually matter. But by convention, just like normally we use X for a variable for solving an equation, I, J, and K are normally what we see down here. So if we look at this pattern here, it's going from 1 all the way to 21, right? So like, how many terms are there going to be? 1, 2, 3, 4, 5, 6, right? All the way up to 21. So there's going to be 21 terms from 1 to 21, right? So now the question is, how do we write the term, the index term, in terms of what we want to put here? So here, the index, this is the first term, right? And what's our first term? Is 1. Well, they're the same. That's good. 2. Okay, our second term is also 2, right? For k equals 3, well, what's our third term going to be? 3. So for our kth term, well, if the first term is 1, the second term is 2, the third term is 3, the 10th term is 10, the 21st term is 21, the kth term is just going to be k. And this is a really awesome way to represent all of these. So I'm just going to do that. K. And that's my answer. The sum of the terms from 1 to 21 of k. All right. We're going to do another one of these. So again, we're going to have our k, and then we're going to have our term. Here instead, we've got 1, 8, 27, 64, 125, and 216. How many terms do we have? 1, 2, 3, 4, 5, 6. And then let's have k. So our first term is 1. Well, that's nice. Maybe it'll just be k again. Our second term, 8. Okay, well, now they're different. So now I've got to figure out, okay, 1, how does 1 turn into 1? How does 2 turn into 8? How does 3 turn into 27? How does 4 turn into 64? How does 5 turn into 125? How does 6 turn into 216? And we want it to be the same thing for each one, right? I want to do the exact same thing from 1 to 1, from 2 to 8, 3 to 27. And hopefully, all of you are noticing, well, wait, 8, I don't know about this one thing, but I know that 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Well, wait, what's 1 cubed? Oh, it's 1. Okay, so if k is the number of the term, then each of these terms can be written as k cubed, right? 6 times 6 times 6 is 216. So now let's actually make our summation. Try to make my sigma as fancy as possible. It's going to degenerate real quick. Don't worry. So we start with k equals 1. And then how many terms are there? 1, 2, 3, 4, 5, 6 terms. So from 1 to 6. And each term is the index cubed. And so this right here is our summation. And that's all there is to it. If you do it out like this, if you write it out like this, it's going to make it a lot easier to see what's going on. It's going to make it a lot easier to put this all together. All right? All right, what comes next? Good. Okay. So here they tell you they're not even going to have you figure out the sum. They're telling you the sum from 1 to n of a sub k is 3. The sum for b sub k is 18. And so the reason I'm showing you this is because I want you to see that summations, you can sort of break them up a little bit. You can always take, if there's a coefficient out front like this, you can always factor it outside the sum. So what this is this is really 3 from k equals 1 to n of ak. Well, we know what that is already. That's 3. So this is really 3 times 3, which is 9. right? Let's do the same thing. You see, it's already not looking so pretty. So BK over 18, well, I can take that 1/18th and I can factor that out too. I can rewrite this as 1/18th of the sum of BK. Well, what is this? This is 18. So this is 1/18th times 18, which ends up being 1. The next thing I want to show you is that you're allowed to break things up over a plus sign. So I can distribute this summation to each of these. So I can make this sum from 1 to n of AK plus sum from 1 to n of BK. Well, what is that? Well, this is 3. This is 18. So in total, we get 21. And then same thing with these, right? This one is going to be the sum of AK minus the sum of BK. So it's 3 minus 18. So this one had better come out to negative 15, right? And then this one, they're trying to be even more extra. You can distribute along the minus sign and then pull that 9 out. So this is really the sum of BK minus 9 times the sum of AK, right? Well, isn't that negative 9? And again, so working with these things is simple as long as you know the rules. Working with these things is simple as long as you know the rules. So speaking of rules, if, just like what we were doing before, if the variable here matches this variable, then there are some special rules, because I don't want to have to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus ain't nobody got time for that. But if you know that you're just adding up k like this, the upper limit is going to tell you everything you need to know, because you're adding up the numbers from 1 to 14. If n is 14, then you're going to do n times n plus 1 all over 2. And these three are important to have in your brain for today's activity. If you can have these written down next to you, then you're going to have a lot easier time. So make sure that this is written down or screen capped or whatever next to you, so that you can call back attention to this whenever possible. So you go through, okay, well, n is 14. I'm just summing k. So n is 14. So I'm going to say, well, this is then therefore 14 times n plus 1 over 2, right? Well, 14 times 15 over 2, that's, well, 14 divided by 2 is 7, right? So let's simplify that right there. 7 times 15, 70 plus 35, this comes out to 105. There's actually a story behind how this one was discovered, by a German mathematician named Carl Friedrich Gauss. And he was at the time like in kindergarten. He was very, very young. And the teacher, not a particularly good teacher, was, the story goes, he just said, he maybe had a hangover the day before, and he came into class, is like, okay, students, for the next hour, you're going to be silent and add up all the numbers from 1 to 1,000. And they're just supposed to sit there and do their sums for an hour or whatever. And within a minute, young baby Carl Friedrich Gauss comes up and hands, here's my answer, Herr Professor, because German, right? And looks at it and goes, Oh God, this is right, because he figured out this formula as like a 5-year-old, and that's the story of Carl Friedrich Gauss. It's probably apocryphal, but that's the story that I remember being told about how this was discovered. The rest of these, not so much. Um, but here, same thing. My n is 14, and I want to sum up all the k squareds, although 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to 14 squared. And I don't want to have to do that by hand. So I'm going to use my formula that I have right here. So if I know what n is, 14, I'll do n times n plus 1 times 2n plus 1 over 6. So we've got 14 times 15 times 2n plus 1. 14 times 2 is 28 plus 1 is 29. All over 6. Well, I can pull a 2 out of here and a 3 out of here. So this is really 7 times 5 times 29. Whatever that is. 35 times 29? Sure, let's do it. 9 times 5 is 45. 9 times 3 is 27, plus 4 is 31. 2 times 5 is 10. 3 times 2 is 6, plus 1 is 7. So whatever this is. This much. If we add up all the squares from 1 to 14, we get 1015. And then the same thing for this one. We're going to do the exact same thing here. We're going to say, okay, we're going to add up all the indexes cubed. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, all the way up to 14 cubed. And again, I don't want to have to do that by hand. Luckily, I have this right here. So I'm going to do 14 squared times 15 squared over 4. 15 squared is 225. Yeah, 225. And then 14 squared divided by 4. The 2's are all going to cancel out, so we're going to end up with 49. So 225 times 49. 9 times 5 is 45. 9 times 2 is 18, plus 4 is 22. 9 times 2 is 18, plus 2 is 20. And then do the tens place. 20. 4 times 2 is 8, plus 2 is 10. 4 times 2 is 8, plus 1 is 9. And then whatever we get here, we add them up. This is the sum of all the cubes from 1 to 14. 1 cubed, 2 cubed, 3 cubed, 4 cubed, etc., all the way up to 14 cubed. You add them up, you get 11,025. Because again, nobody wants to actually physically count those. And if we have these formulas, they will make our lives so much easier. All right? So take a look at this one right here. Well, let me look at this and go, oh, well, I don't know how to do when there's times. Let me distribute it so that I get what I want. So we've got the sum 1 to 5 of 9k squared. And we can split along the plus sign. I'll just do that automatically, plus 5k here, right? The only thing that is forced to stay inside of the sum is k. Anything that is not k can come out. Even if it's another letter, like we're going to end up where there are going to be k's and there's going to be n's in our problems later on. So if there's an n, but our index is k, we can pull the n's out because they're constant with respect to k. And I'm just going to pull out the 9. And then remember, the k squared is n plus 1, 2n plus 1 over 6. Right? And then here we've got the 5 just pulls out, and then the sum of the k's is n plus 1 over 2. So k is 5, n is 5, so let's do that. 5, 6, and 11, right? 5 plus 6 plus 11, or is that 22? 5 times 6 is, oh wait, this is not plus, it's times. Oh goodness. Haha, 5, 6, 11 times 6. Again, this is why it's always important to double check your work. Always double check your work. 5 times 6 is 30. So we got, so let's simplify this. The 6's cancel out in this one, leaving us with 55. So 9 times 55 plus 30 divided by 2 is 15. So 5 times 15. So we got 75 here. And 55 times 9. I don't feel like trying to do that in my head. 5 times 9 is 45. There we go. 495 plus 75 is 570. So notice what we did. First things first. When I've got something troublesome like this, break it out, make it into a polynomial like 9k squared plus 5k. Then you can break it up. Remember, you can always break up across a plus sign. You can't break up across a times sign. So make sure that you get it all into discrete plus sign things. And then I know how to just pull out numbers. This right here turns right into this. This right here turns right into this, and then we can just plug in and get our answer. Don't overthink this. This is once you see what to do, it's mind-numbingly simple. It may require a little bit of writing, but it is mind-numbingly simple. All right, the last one I wanted to show you, I want you to notice something. There is no letter in our index. We're just taking the number 2 and we're adding it up 7 times, right? So I want to tell you, if you've got something like this of some random thing, whatever, that has nothing to do with k or n, you can just take this and multiply it by that. So whatever this is times whatever this is gives you your answer. Again, if you tried to add 2 up 7 times, you definitely get 14. 2 times 7, a 14. Same thing here. If I added 7 up 300 times, that's just 7 times 300. Same thing here. If I took 10 and added it up 264 times, but I'm missing the bottom 2. So here's what we can do. We can say, all right, well, I got to subtract 210. So I'll do the 640, right? 10 times that is that, and then I'll minus the 2 that I'm missing, because I'm missing k equals 1 and k equals 2. So 10 and 10 makes 20, right? So then I can just subtract and get 26, 20 for my final answer. Always, always, always pay attention to that bottom index. I say that knowing that I'm going to mess it up half the time because I don't pay attention. I'm telling you so I can hear it in my own voice myself, okay? Because it happens to me all the time. It does. All right. Now, we've done all of this. Now it is time to talk our way through a Riemann sum. All right? So, let's get rid of you. Let me scoot you down first so I can read it. All right, so we're trying to calculate the area under a curve over a region. So what we're going to do is basically like what we did last time, right? We said we're going to figure out the width of each rectangle, we're going to figure out the height of each rectangle. Before, we could just be like, okay, well, we're being told how many rectangles that there are, and we know the range, so we could just be like, okay, well, if it was from 3 to 5, and I needed 4 rectangles, and each rectangle is going to be 5 minus 3 over 4, right? Because from 3 to 5 has a length of 2, and we want to split that up into 4 pieces, so each one of those is going to be 1/2, right? So that's the idea with this, except now we don't have numbers to deal with exactly. So what I want to do is I want to give you the formula so you can see what the formula is. Write it down so you have it. The Riemann sum will look like this. K equals 1 to n of f of the kth term times the change in x for k. Now, we're going to have better things for this in a little bit. Specifically this one, because this delta x sub k, that's going to be just like what we were doing up here. B minus a over n. N is something we're not going to worry about, but B and A are things that we are going to identify, right? Here's our A, here's our B, right? So B minus A over n, well, B is 1, A is 0, and n is just n. So our delta xk is 1 over n. So to review this little part that we just did, this is what we're always going to be doing. We're going to say, all right, well, let's find what B is, let's find what the A is, subtract them, put them on top of an n. So B was 1, A was 0, subtract them, and then that gives you your width of every rectangle. Now, what about this thing? Well, we know what f of x is. They tell us it's 5x plus 7x squared, right? But now, what we want is we want to get that in terms of the right-hand value of the function for some value n. So all we're going to do is we're going to figure out what ck is. Well, any given term, ck, we're starting at a, right? So we'll start at a. And then for each successive rectangle, we better be adding 1 over n. Well, how many times do we add 1 over n? K times. So let me give a more general formula. So we have it b minus a over n times k. So this is what's going to go into our f of x. This is what we're going to plug into f of x. All right. So what that means is we're going to take this, which let's actually plug everything in. So this a is 0, b minus a is 1. So we've got really 1k over n. So this is really just k over n. A lot easier than this, right? Because a is 0 and b is 1. So we just put a is 0, put b is 1, and then simplify it down. So basically, wherever we see an x, right, this is where x is supposed to go. Wherever we see an x, we're going to put a k over n. So what this turns into for this problem is plug in k over n, plug in k over n, 5 times k over n plus 7 times square it, right? K squared over n squared. And then we're going to multiply that by what? Delta xk, which is 1 over n. This is our Riemann sum. Now all we're going to do is we're going to take it and put it together. So what do we do? What do we do? We're going to do at least one more of these. I've got at least one more to work with. So let's go ahead and do this. So we've got distribute the 1 over n in, right? I'm gonna start to be messy. So we got 5k over n squared plus 7k squared over n cubed, right? And we can remember we're allowed to distribute over a plus sign, and we're allowed to pull out anything other than k. This is, remember, k equals. Okay, so let's do that. We got 5 over n squared times the sum from 1 to n of k plus 7 over n cubed sum of k squared. Well, we know how to do that, right? There's k and there's k squared. So let's bust this out. So we've got n times n plus 1 over 2 So just going to put it all together like that, right? The 5 and the n squared are here, then the n plus 1, and the 2, right? And then same thing, 7 times n plus 1 times 2n plus 1 all over 6. And then don't forget about the n cubed that's already down there. So I've broken it out of its summation. All the sums are dead. The only thing that's left is the number of rectangles. So in theory, if I had any number of rectangles, I could just plug that in and see what my answer was. But those would all be approximations. I want there to be so many rectangles that I have the exact area. So what am I going to do? I'm going to read what it says. It says, then take the limit of this sum as n goes to infinity. So if we take the limit of this, well, a couple things to notice is that all these plus ones are going to go away because we're in infinity land. N gets too big, right? So what we really have here is 5n squared over 2n squared, right? The plus 1 went away. Same thing here. The plus 1 goes away, and I'm left with 7 times n times n times 2n, so plus 14n cubed over 6n cubed. But what's going to happen to those n's? They better cancel out because I'm trying to get an area, right? The n's should go away, right? They cancel out here. I'm left with 5 halves. They cancel out here. I'm left with 14 over 6, which is, and then if I add those up, 5 halves plus 7 thirds, so 15/6 plus 14/6 is 29 over 6. So let's do one more. Same exact thing, just with different variables this time. Okay, so here we're going to find the sum 9 minus x squared and we're going to find it, the sum under that curve from the region at 0 to the region at 3. Right? If you think about it, it sort of looks like it's an upside down parabola, shifted up 9, right? And so we're going from 0 to 3. So we're trying to find this sort of right here. This, how big is this? So let's do that. Same thing we did before. We got to find CK. We've got to find delta XK. Well, what's CK? CK is that XK is this. So A is 0, B is 3. So CK ends up being 3 minus 0, 3 K over N. XK ends up being 3 minus 0, 3 over N. Well, now we have everything we need. Let's plug this into f of x. And then multiply it by our delta xk. And then let's go to town with it. So we've got, once we distribute everything in, we've got 9 times 3 is 27 over n, right? 3 times 9 is 27 minus 3 squared, k squared n squared times 3 over n. So 3 squared times 3, again, 27. K squared over n squared times n is n cubed, right? So now, same exact thing we're going to do. We're going to break it up. We're going to pull everything out, and we're going to move on with our lives. So this 27 over n just pops out. And remember, the top here is n, so we take this, multiply it by n, since there's no k in here, right? So this is just 27 divided by n times n, which is just 27 minus. And then we're going to pull out the 27n cubed. And then we have to deal with k squared, right? N times n plus 1 times 2n plus 1 over 6, and multiply all that together. But we're taking this to infinity anyway. Let's just move on from here, right? When we go to infinity land for n's, the 1's cancel out, right? So what are we left with? 2n cubed, and this should be over n cubed, sorry, because that's right here, right? N cubed, yeah. Nope. What am I doing? Okay. So what do we have? 27 minus, we've got 27 times n times 2n. So times 2n cubed, n cubed times 6. So look at what we have. We've got 54 divided by 6, right? 54 divided by 6. It's just 9, isn't it? I hope so, yeah. And then the n cubes cancel out, so we're just literally left with 27 minus 9, right? That had better be 18. So the hard part of this is remembering how to work with the summations. If you can do this part right here, and you can do this part right here, if you can get to here, everything else is very simple because we're just taking the limit, right?